Okay, so today, as I was saying, we will be talking about the structure of proton in this class. Now, before we talk about this structure of proton, I would like to recapitulate some very old things. Say for example, suppose this chalk here. So this is a very small piece of chalk. Now, if I ask you what is the structure of this chalk, it will depend. If I ask a physics student, he will answer in a different way. Suppose I ask the same thing to a 2-year-old child. 2 বছরের বাচ্চাকে জিজ্ঞেস করলাম, বাবা এর ভেতরে কি আছে বল? What will he do? He will just take the chalk, put it on the table, take one of his toys and just crush them. Okay. Why? Because this is what he does. The child, you will see, when he destroys a toy, it is basically his way of trying to understand the world. How is the world working? How is this toy working? How is it alive? Or something like that. Now, the boy has just demonstrated a chemical technique. We can also do this something like this. I am taking this chalk, I rub it, and you will see small dust particles coming out. Okay. So this is how you can just get a macroscopic view of this chalk. So there are small dust particles. Now what about lower dimension? Suppose I see it with a microscope, or even better, electron tunneling microscope. What will you see? What will you expect? We do know as a physicist that basically below molecular structure we have atomic structure, then we have nucleus, and then even below we have the quark structure. This we know. But let me first talk about how this whole journey of this structure of proton we will proceed. Now, the thing started with the birth of nuclear physics when Lord Rutherford he did his famous experiment, Rutherford scattering experiment. So, basic idea was to bombard a neutral matter, a sheet of neutral matter with a charged particle, say alpha particles. It can be neutral as well, but you will not be able to accelerate it. Right now, so alpha particles were bombarding on the gold foil. Now, what is the significance of the observation? The significance of the observation, as you were just saying, is that few out of large number of particles were getting rebound, and from there Lord Rutherford he given a sort of explanation that nucleus is there. But to be more convincing, let me give you a different sort of analogous example. Suppose I have this a dusty piece of paper somewhere, right? Now I put a machine gun in my hand and I start shooting at it on this just piece of paper. And you must be thinking this is ridiculous, right? A bullet is this much thick and the piece of paper is very thin. What will happen? It will just pierce the thin paper. But out of what Rutherford observed in his experiment was that out of a large number, very large, you have to find out how large it was. Was it of the order of 10 to the power 4, 10 to the power 5, 10 to the power 6? The more larger the number, it means more smaller the dimension of the thing which is able to rebound the alpha particle. Understand? So out of those large numbers, few bullets they come and hit me back and I am injured because of this. So the first thing that I will think is, how dare you piece of paper, you hit me back? If I just blow away some wind on you, you will be flown away. Now how dare you hit me back with the bullet? This is the analogous logic. Okay, Okay, so there must be something inside which is very compact, very high density, and it is able to rebound your alpha particles. And there, from that logic, basically the existence of nucleus came into being, and plum pudding model was forever gone. Now the fact is quite similar to this blackboard. Suppose I give you a piece of matter, something like this much matter, and think that I am asking you to make a two-dimensional sheet of this matter such that the density will be very high and it will be able to rebound a bullet. What will you do? The very first thing that you have to think of is that if I choose this much matter, something like this on the blackboard, the density will never be high and the bullet will just pierce it. So what you have to do is you have to compress the matter in certain parts and there will be gaps in between, and this is how you will get high density zones. Although the piece of blackboard will be very empty, but there will be certain very high density zones, and if you put a machine gun and you try to hit the bullet, then most of the time the bullet will just pass away from the free space, similar to the atom. Atomic dimension, angstrom; nuclear dimension, Fermi. So compared to the nucleus, compared to a proton inside a nucleus, the electron is 10 to the power 5 meter away, rough, 10 to the power 5 times far. So there is so much space, so the bullet will just go in. Any charged particle thrown away will go in, but there will be a chance. A very small few, we will just hit the nucleus, or in our case, the blackboard, the high density zone, and then they will be rebound. So this was the origin of the few rebound cases in your Rutherford scattering experiment. And so basic idea was to bombard. Now this is a gold plate, right? And alpha particles. Now here you see, here we have nuclear force, which is putting this alpha gold nucleus together, and this is also a strong interacting particle, but also this is charged as well. So in this interaction, in this scattering, both electromagnetic interaction and nuclear force is coming into play. Okay. Now what we will do in order to understand the structure of proton is we will bombard the proton with something which is purely electromagnetic in character. No strong interaction, nothing. So what is the best example out there which can be readily accelerated to very high energies? It is electron. Right? And also you know from your basic understanding, you remember the anomalous magnetic moments of proton and neutron. So magnetic moments means there must be some sort of current-like structure moving on inside. But the proton is just a proton. How can you have a magnetic moment? So this fact itself means that the proton has some structure, something inside, some charged particles which are moving around. And as a result, you are getting this anomalous magnetic moment. But you don't have so for electron. This means electron is a point particle. Okay. So this is the first idea that you have regarding the proton. So this means the electron is a point particle, a proton has a substructure. And so we will be using the electron point particle in a scattering experiment. Physicists, they don't dirty their hand most of the time, like this rubbing or hammering of the chalk the child was doing. Suppose I ask you what is the temperature of the sun, you will not go there with a thermometer measuring, even if it were possible to do so. What you will do? You will ask me, sir, give me a piece of paper and pen. You will use virial theorem, and from there you will estimate the virial temperature. Just like that. Use a principle. So here, what we will do is, we will use the principle of scattering to understand the structure of the proton. Now before that, let me ask you something even very simple. You see, I am talking about this structure of proton. right? Now what about when I am drawing this on the blackboard? I am drawing this diagram, not diagram, I am drawing this very simple electron, I am writing all that. Where is your famous nuclear physics? Here, right now. Where is the strong interaction? What is its role in drawing this? So this is my question to you. What is the role of the electromagnetic interaction or a strong interaction when I am drawing this? Where is it? The answer is that the forces are inside. Because of the nuclear force, you are able to, the very simple chalk particle inside this. It will have carbon, oxygen, nitrogen, very type of atoms together in a molecular structure. Now because of the strong interaction, those elements, those atoms, those nucleons, they maintain nucleus, they maintain structure. And remember, when I am doing this explanation, I am writing, the strong interaction doesn't come into play. In fact, entire molecular physics, molecular spectroscopy, you can explain without invoking your strong interaction, without even thinking about strong interaction. So this means that the range of strong interaction is very small. Okay, so here also no strong interaction. But remember, the strong interaction is there, of course. That's why the chalk is chalk. That's why I am what I am. Now let me ask you something. Suppose the range of strong interaction, you know, its range is lower than Fermi range, 10 to the power minus 15. Suppose instead of 10 to the power minus 15, the range of strong interaction was 1 meter. What will happen? Question. Bolo. Can we do the class like we are doing? প্রথম প্রশ্ন, আমরা এইভাবে কি ক্লাস করতে পারতাম যদি স্ট্রং ইন্টারঅ্যাকশনে এরকম রেঞ্জ থাকতো? দেখো, রেঞ্জটা যদি ফার্মি অর্ডারে না হয়, if it is not of the order of Fermi order, it is much higher. Then what will happen? The different nucleons, that inside this chalk we have got so many atoms, each made up of different elements, right? If the order is of 1 meter, what will happen? All those atoms, they will just combine into one big atom together. There will be no distinction, there will be no variety. The entire world will be just become one single nucleus. Understand? No different variety. Kono chalk থাকবে না, kono board থাকবে না, আমরা থাকবো না, তোমরা থাকবে না, কিচ্ছু থাকবে না. It will be so boring. This colorful, rich life that we have is because of the manifestation of this small interaction range. You must remember. We don't normally say like this, but this is very important to know. It will be like a black hole scenario. It is eating away everything. Something like that. So we are very lucky that the range is not so. Although we have to go through a lot of troubles. You will soon see so many equations in order to just understand this. But it is at least better because we are here to do this, right? Otherwise, if the range is higher, we will not exist. Okay. So basic principle. So I have just talked about Rutherford scattering, all that. I have talked about the importance of the range of strong interaction and also how difficult it is. You see, when I will be doing the scattering experiment, so basically I will be forgetting about the nuclear effect right now. Only electromagnetic effects will be here using this. So instead of electron, if I have to bombard a proton with a proton, what will happen? Both electromagnetic and strong interaction will come into play. Right now I am not talking about that. Let me forget the strong interaction part. I don't want to get bothered with it. Let me first just single out the electromagnetic component of it. So I use a pure electromagnetic probe, electron, a very high energy one. বুঝতে পারছো? High energy electron. Now what will happen if the energy of the electron is very small? What will happen? Elastic scattering. your Rutherford scattering, right? Something like this. কি হয়েছিল যখন Rutherford scattering, when we did alpha particle, as you increase the energy, you have seen, right? As you increase the energy of the alpha particles which are bombarding on the gold nucleus or any other heavy material, foil made up of material, what you will see, initially the cross section is that of Rutherford, that means elastic Coulomb scattering. But later on, because of different nuclear interaction, the cross section nature changes. Here the same thing will happen. But you will ask me, sir, how is it so? There is no nuclear interaction over here. How will the cross section change? The thing is that at first we will have only electrons elastic scattering due to electron. Later on, now elastic scattering, this means that you see the interaction. I am talking about charge particle interaction, right? Now in quantum field theory, which is a much better theory than your single particle quantum mechanics, this electromagnetism is basically, you can think of it as this mediation by a photon, virtual photon, and because of that we have got, you can see, one charge can feel the presence of another charge. So basically we have got the mediation. This whole interaction will be happening through virtual photons. Now why virtual? Because we will be creating those photons, not we, nature does, and that is also following the uncertainty principle. They are not real photons. Real photons exist all the time, but virtual photons, you know this, right? Particles, force particles. Okay, what is the, for nuclear force, what particle is there which is mediated? Pi meson, pion. What is the mass? 140 MeV, right, per c square. This is the mass of the pi meson. If the mass is lower, range is higher. Photons, what is the rest mass of photon? 0. So that's why electromagnetic interaction is infinite range. Okay, so initially we will be just having elastic scattering. So at that time the wavelength of the virtual photon, initially when the energy of this electron is low, the energy of the virtual photon, the wavelength basically will be much higher than the dimensions of the proton. Now as you increase the electron energy, as a result of this, I am talking about single virtual photon interaction, not multiple. What will happen is that the wavelength will keep on decreasing, and very soon at very high energies we can have inelastic electron scattering. When the virtual photon's wavelength becomes lower than that of proton, then it will start seeing the internal structure of the proton. And at very high energies, what will happen? You will not see like this. Basically, you will see something like this. So, internal structure of the proton at very high energies. This is what the virtual photon will be seeing inside the proton, and then it will interact with one of the point particles, and we will see as a result of this interaction again a sort of elastic scattering, but this time not with protons but these very point particles known as partons. Okay, and later on it was known that these point like particles are basically quarks and gluons. So this is how the thing is evolving. This is what we will be doing in this class. So we will be talking about the existence of these partons through the scattering of electron on proton. বুঝা গেল? আমি যেটা বলছি এই প্রথমে ও কিন্তু একটা পয়েন্ট প্রোটন দেবে যদি ওর ওয়েভলেন্থটা খুব বড় হয়। এবার ওয়েভলেন্থ অফ দ্য ভার্চুয়াল ফটোনের ওয়েভলেন্থটা বড় হলে পয়েন্ট তুমি বলো না লাইটের ডিফ্র্যাকশন যখন হচ্ছে ওয়েভলেন্থ, ঠিক তো? আমার ওয়েভলেন্থ যখন অফ দি অর্ডার অফ ডাইমেনশন হয় তখনই তো ওই জিনিসটা প্রুভ করতে পারে। right? So the virtual photon's wavelength, when it is of the order of proton dimension, then only it will be able to see inside the proton. And if the wavelength of the virtual photon is larger, তাহলে কি দেখতে পারবে? দেখতে পারবে, আমরা একটা point particle দেখবে, and you will see a elastic scattering with just a point particle, which is a proton, right? কিন্তু যখন আমি এনার্জি বাড়িয়ে দেবো, ও কিন্তু সাবস্ট্রাকচার দেখবে, and এটা তোমরা দেখবে deep inelastic scattering এ you can explain the entirety of the deep inelastic scattering, that means very high energy of the electron, assuming that the interaction is just taking place with point-like particles inside the proton, and they were given the name proton by Richard Feynman. He was the one who devised this model. So basic quark parton model. So this is what we will do in our class.